to, we can go over all your questions to the homework when we get back from Thanksgiving break. But we gotta rip the rest of this out. So this first part is something we did look at earlier this year, which is sometimes you have to use Zoom on your calculator because what you see is not what you get when you need to do the math on it. And we had kind of started on this one. Just talking about where we know the end behavior is going to go with a positive leading coefficient x to the fourth. We expect this. That's a good question. All I can tell you is example 8 because I don't have page numbers.
18.
So, you don't have to punch this in if you want to just follow along because I knew we were time crunched today. I cheated and I put all of the equations that we're going to need in here already. And if we do Zoom 6, that's what we see. And obviously that's not a good view of what's going on because if this is x to the fourth, we expect there to be, either 4 real zeros or 2 reals and 2 imaginaries because imaginaries always come in groups of 2s. And we see, hey, this is the behavior we're expecting over here. We also see negative 3, 0 is looking like a 0, but we would do second trace, and we might change the window a little bit, but more important is that we're able to just find these zeros. Oops, I'm way up there now. Okay. There was the left. There's the right. So zeros at negative 3.0, well, 100 probably. And we might want the y-intercept just by quickly putting a 0 in all of these positions and seeing that that's going to be 0, negative 2.4. I'm going to change the scale on this one because we really just want all those important points. But now, Zoom box would be a great thing to use for this section. And sure, over there where the zeros were. So I'm going to make a box around this because it doesn't look like I'm getting all the zeros that I need until I can see exactly what's going on in that region. And I see there are 3 zeros there. So second trace, number 2, get this little bugger, which looks like it's right at 1, but we'll find out for certain. Oh, 0.5, that one's going by 1s across there for the zoom. So right about there, second trace, number 2, get this little 0. 1.133, 0. Second trace, number 2, one last 0 to go. So below it, right arrow above it, 1.3670. And then again, we know the end behaviors. The one thing we would have to use the graphing calculator for that's left is where's the top of that little hill, That would be the last thing that we would grab that for. But we're looking at this end behavior, and it matches what we know. We'll go back to Zoom 6 so we can get that overall look at the graph again. So heading down, coming back up, zipping around, and away we go. And the important stuff for us to find is truly those zeros, because a lot of times we can do that algebraically. The y-intercept we can usually do algebraically. Let's grab the calculator when it's not factorable, and find those zeros and that local max. Like I said, I don't want to take the time to do it right now, but that local max would be another point where we would identify that, because this was just find all the real zeros. So now, what do we need to do with it? Well, this page, I guess, didn't even get in your packet somehow. Okay, I'll pass that out later. But let's talk about our designing box problems. This is engineering right here, folks, is what this is. We have a plant right outside of Elk River on the way to Anoka called Protec Engineering that creates the machines that take big pieces of cardboard, chop them up, folds them up, glues them for places like General Mills for cereal boxes and all that kind of stuff. So Dixie Packaging Company has contracted to make boxes with a volume of approximately 484 cubic inches. Squares are to be cut from the corners of a 20 by 25 piece of cardboard, and the flaps are folded up to make an open box. So, visual. There's our box. They're going to cut these little square corners out. Well, that doesn't look like a square down there. Little squares out of there. Right now it's 20 by 25. But they're going to cut some amount, I don't know what it is, some amount to make those little squares in the corner. So it says what size squares should be cut from the cardboard to give us a volume of 484. Well, volume means we're supposed to use length times width times height because this is a box. So volume would be, well, it was 25, but they're going to cut these two x's out of here now. So it's going to be 25 minus 2x. And this was 20, but they're taking two x's out of that one. And then you have to visualize folding the box up. You need the height. What is the height? It is x. I mean, that's what we don't know. And they want to know, when is this 484? Technically, we wouldn't even have to multiply all of this out. The calculator will get us everything we need. Again, you can just watch this one if you want to. So I'm going to turn this one off. And now we're down here at 20 minus 2x times 25 minus 2x times x. I'm turning that one on. And I'm turning the 484 on. Because what we want to know is the intersection between these two. But the thinking part is right here, window. Okay, what should I be using here? Well, we don't want the volume to be 0. And if 25 minus 2x is 0, we don't want to use that. So we start thinking, if I was to solve this, I'd get 25 halves, which would be 12 and a half if I solve it for 0. If I solve this one for 0, that's going to come out to be 10. So I definitely need to stick to below 10. You know, that's the only way this is going to work, because otherwise I'm going to have zeros in there or a negative. So 0, 2, bless you, 10. And then I know I want to see 484, so maybe I'll go to 500. And there are actually going to be 2 spots where they could cut that X piece out to 2 different sizes. So second trace, number 2, where is Blinky? Blinky is there. I'm going to get the left one first. Both is closer to go with the right one. But this is intersection. Uh-oh. I think I hit number 2 instead of number 5. Number 5, intersection. Okay, Blinky, right over there. Tell me where that is. Blinky says it's at 1.2222 Steph. And notice we get the 484. Second trace, number 5 again, getting Blinky over to the other intersection so he knows I'm not still talking about that same intersection. So Blinky, it's that one this time. Find it. 871. 6.871. So it says, what size squares should be cut from the cardboard? Well, they'd have a choice. It could be 1.222 inches or 6, 5. 0.871 inches. Either one. So what we saw, and just a sketch we'll do here, was that this is going to hit in a couple of spots. And maybe I'll try to get the 6.87 right. 1, 2, 3, 4, 5, 6. Hitting in 2 spots. And both of those spots will work. It's just a matter of what would your clients want the box to look like, you know? With the 1.22, it's kind of going to look like a pop case, big bottom piece with the 1.22 coming up. But with the 6.871, more like a cereal box because it's going to be taller and skinnier. So it's whatever your customer would want is what you're going to use. And since they didn't tell us, we have to just say, hey, it's those two. That's it. So now, this one says, example 10, an open top box is made by taking a piece of cardboard 20 by 40 centimeters, cutting squares on side lengths and folding up the sides. And we are to write an equation of a polynomial function representing the volume of the box in terms of x. So they're telling us use this notation, v of x, you know, volume of the box. So given that we just did that one, talk me through it. What should we put for those dimensions? 2. There it is. Now I am going to show you what this is multiplied. If we did all of this, we'd have v of x equals, comes out to 4x cubed minus 120x squared plus 800x. And I know all of you are capable of FOIL and then distributing an x, so I'm not worried that you're not going to know how to do that. C says, what is the domain of v of x? Well, technically, if you don't know this is about volume, you can use whatever numbers you want in this. I mean, it's a function, so we could say technically the domain of v would be negative infinity to infinity. But then it says for what values of x would v of x be greater than 0? Well, we know we can't have negative pieces. So the more important question is this one right here. What is the relevant domain? The relevant domain is what would work for this problem. So for d of v with a relevant domain, take a look at these two in particular. Obviously we want to start with 0, but what should be our highest value for our x's? 10, yeah, because of this one right here. Would give us 10. This one would give us 20. We have to take the smaller one because a 20 would make this negative. So we find the one that basically gives us that smallest 0, which is going to be 10. Now, the book argues that we should put this down. I would argue, why include 0? Why are you even trying to find the volume if x is 0? So the book used the closed bracket. I'm on the side of why on earth are you even doing this problem if you've got a 0 in there? You know? So again, they're kind of all over the place with their brackets. I do the 0 to 10. And this one says, if the volume of that box comes out to 1500, show that the box can be constructed in 2 different ways. So basically we want to see that our graph is going to hit that in 2 different spots. So we want to see that 1500 equals our 4x cubed minus 120x squared plus 800x. Now, again, you wouldn't have to multiply all of that out. So I'm going to turn off the one we were just doing and turn on the 1500, and notice I did not even multiply all this out, just like we did the other one. But we already set our window by talking about that relevant domain. We have so little time together. We could focus. We know that our y is 1500, so maybe we do 2000. I just left it with the parentheses in there. Make it easier to punch in. So there they are. We can see that there's 2 of them. Again, we do second trace, but number 5. Let Blinky find those intersections for us. And Blinky says at 3.486, we get 1500. And over here at 5, we would get 1500. And these were in centimeters. So our sketch to show that we understand that this is going to hit is going to be the fact that we're putting that 1500 on there somewhere, and that this is going to hit at 3.486, 1, 2, 3, and some change, and at 5. That would be our graphical evidence that there are actually 2 spots. And the second part of this is just, okay, so now you've got your customer sitting in front of you, and you tell them they have a choice with 3.486 and 5, and they say, what are they going to look like? Well, you have to be able to give them the other dimensions. It's not a tough thing to do. We go back up in here, and we put our 3.486 in here for x, put it in here for x, and obviously the 3.486 is definitely going to work for that last one. So with the 3.486, what do we end up with here? 13.028 centimeters. By, and then the other dimension was 33.028 centimeters. So those would be our dimensions if we used the 3.486. Come on, smart work. And then the other one was 5, and obviously that would be easier to put back in there and do your 40 minus 2x. So that one's going to be 5 by 10 by 30. Oh, and I know I ran out of space, so this would go back up. Because D says, maybe the customer says, you know what, just maximize the volume for me. Make it hold as much as it can possibly hold, and that's what I want to do. It is the vertex. So for that one, you could just go to the maximum, which will be number 4, and left side of the hill, right side of the hill. Oops, I went too far. I'm just going to write it down. 4.226. That's what you guys got. Those of you that were punching it in, I hope. And then again, you'd put those back in, and that would be by 11.548 centimeters by 31.548 centimeters. So if they just said, make it hold as much as it possibly can, we don't really care if it's big and fat or tall and skinny, just make it hold as much as it possibly can, then that's what we would use. All right, and the last piece of this is calculator stuff. So if you do have a calculator, let's actually put these in. It's not going to take very long, otherwise I would have just plugged it in and told you to watch. Go. And that's because we know our calculator does more than just linear regression. We can do linear regression, quadratic regression, we can do cubic regression, we can do quartic regression, all kinds of things. So any 2 points in the Cartesian plane by the point line plane postulate gives you a line. So with different x values and different y's, determine a unique slant line and its related linear function. Any 3 non-collinear points give you a quadratic. So you start thinking, well, maybe there's a pattern there. 2 points, you get a line, which is a first power equation. If you have 3 points, 3 minus 1 is 2, and you get yourself a quadratic. It absolutely is a pattern. So basically, you take the number of points you have and you subtract 1, and that'll get you a perfect fitting polynomial. So in general, n plus 1 points positioned with sufficient generality determine a polynomial function of degree n. The process of fitting a polynomial of degree n to n plus 1 points is called polynomial interpolation. Polynomial interpolation. And exploration 2 has some very nice numbers and not very many of them, so we can certainly get through these. So the first one, I look at this and I see there's 1, 2, 3, 4 points. I subtract 1, that makes this a cubic. So I should do cubic regression on those little buggers. stats, edit, and yeah, I did cheat, but I'll give you guys some time to get those in. Put your X's in as list 1, your Y's in as list 2. Far's good. So then stats, this time we are going to calculate, this is going to be cubic regression, which is number 6. And we get y equals 0.006 x cubed plus 0.018 x squared minus 0.501 x plus 0.977. But here's what's important. Look at r squared. What would r be? Perfect fit. Perfect. So if you take the number of points and you subtract 1, you're going to get a perfect fit. So number 2, they're giving us 1, 2, 3, 4, 5 points. And I wish they wouldn't have told us it was quartic, because we can certainly figure that out, because 5 minus 1 is 4, and a quartic will be perfect. So let's get that one. And then you'll go to stats, calculate, but this time we're all the way down at number 7 for quartic regression. We'll just arrow down once on the main screen to say, woohoo, perfect fit again. And it will be. So we should start thinking, okay, so can we do beyond quartic? Stats, calculate regressions. I've got linear, quadratic, cubic, quartic. That goes back to linear, but then we have the natural logarithm regression, exponential regression, power regressions, logistical regressions, sign regressions. And yeah, some of them we might have to do manual fit. We won't do. The ones that we're going to do in here are going to be usually quartic is about as high as we go for any of those. So that's an easy find. But the question that really was huge here was, these are a perfect fit. I mean, that's excellent. So these are perfect fit polynomials. These are perfect models. That's a big deal. You know, when you can get a model that fits all of the data perfectly, that's exactly what you want. So why doesn't that happen all the time? Well, because if you have 2,000 pieces of data, chances are pretty good something's not going to fit in perfect with what you're doing. And there's always outliers. If you guys remember that from stats, outliers are the people that answer the question weird or throw your data off. Those are your outliers. So always try to pick a model with that least possible degree. There we go, lowest possible degree that has a reasonably good fit, which means you maybe give up your 1, but you get something pretty close. So now we do have to go back to the piece that was not in your packet, which kind of threw us all. We're like, why are we going back in here? We have to cover that. Because a big part of the day 3 assignment is writing polynomials. And they assume that you remember all the writing polynomials that you did in Algebra 2. But my guess is that some people have maybe forgotten how to write polynomials. Because it's been a while. All right. Usually the directions of these will say, find a polynomial with least degree that has the following zeros. And that's what we want to do, but the instructions are here just shortened a bit. So find a polynomial with zeros at 2, -3, and -4. This all comes from backwards thinking. And that backwards thinking is, where did that 2 come from? Okay, that. If we put a 2 in there, that's a 0. -3 came from x plus 3. Now the format you learned in Algebra 2 was the x minus h piece, you know? So this is what it would be. And it is supposed to be a polynomial function, so we'll just call it f of x. Y would not be wrong, it was not stressed up there that it's a polynomial function. But this is foiling and then doing some distributing. So I would FOIL the back 2. And then do the clamshell distributing. And then you get that big clamshell. So we have x to the third plus 7x squared plus 12x by distributing the x through everything. Where people usually make mistakes is with the negative. So be careful when you go through. -2 times x squared is -2x squared. -2 times 7x is -14x. -2 times 12, -24. And then if we are lucky enough to have a couple of like terms to combine, then we should do that. So x cubed, but 7x squared minus 2x squared is plus 5x squared. 12x minus 14x would be minus 2x minus 24. Easily enough checked. I mean, all you have to do is put your new polynomial into your graphic calculator and make sure that it will cross at 2, -3, and -4. And if it doesn't, then you go back and figure out where'd you goof up. But when do they get harder? When we have radical or imaginary solutions, they get a little bit harder to write. Not a lot, if you know what you're doing. So we look at this and say, all right, I'm going to call this one g of x this time. The 2, not a problem. X minus 2, got that. Ew. 1 minus the square root of 3 and 1 plus the square root of 3. Seriously? But yeah, we treat them the same way. We say it has to be x minus 1 minus the square root of 3 and x minus 1 plus the square root of 3. But now we also know we have to be careful with those negatives in front of other things. So we'd better distribute those negatives inside there and see what we have. And now, what a mess that would be, multiplying those two together, right? I mean, that's a heck of a clamshell when you've got 3 terms in each one of those. So maybe we can make that a little easier, you know? And here's how we do that. We notice, oh, we both have x minus 1s now. Let's make this a little easier. Let's chunk those two together and make this work a little better. Because now, notice how the chunk is the same, and the last term is the same, and the middle terms are going to cancel out because 1 is plus and 1 is minus. So we won't have to do outside times outside, plus inside times inside. So we've got x minus 2 just waiting to do its business. But here we'd have x minus 1 times x minus 1. Well, you could either FOIL that or you could remember the pattern. We'll give you x squared minus 2x plus 1. And then we know outside times outside and inside times inside are going to cancel out, so I'm not bothering to write those down. I'm going to go to the back. Positive square root of 3 times negative square root of 3 is negative. Square root of 3 times the square root of 3 is the square root of 9. That's 3. But hey, those parentheses aren't doing anything anymore, so might as well see what's going to happen if I drop them.
That's the last problem, which we didn't have any trouble with at all.
So the grouping makes this so much easier to do. And it would be a little harder to check this one, you know, and that's just because we had those radicals in there. So we would probably have to do, thank you, finding the zeros with a little bit of second trace and making sure that that's really 1 minus the square root of 3 and 1 plus the square root of 3. But do you see how much easier this problem is by grouping that up and just manipulating it a little bit? Yeah, that makes it a lot easier to do that problem. All right, so I'll give you the assignments, and I better see what time we get hubby in. Okay, so I will have to wait to take homework questions until we come back, so you can just kind of store those up. But now you'll be able to do all of this, thank goodness. And what else are you gonna do by Thanksgiving?
Project.
Yeah, your Google technology slide, your Google slide. Again, when you go to put your link in, start by going to the form where everybody's name is on it, pick the cell, and then do create link. And that'll just kind of guide you all the way through. Because some other students in Mrs. Peterson's class had said they already tried to do it by making the link first and then putting it in there, and it didn't show up right. So go to create a link in those cells. Let's see. And remember to check each other's, you know, remember that your partner's hanging out there waiting for you to give them some good comments. Never had so many green passes as I've had today, boy. All right, reminder, because I know you guys are